Hello, AP Chemers. So we've already talked about solubility equilibrium, and we also talked about Q and K and comparing them, and how you can use Q to figure out where you are in the reaction if you're at equilibrium, or if you're going to proceed to the right or to the left in order to reach equilibrium. Let's review that real quick. If you calculate Q, and it turns out to be equal to K, and in this case we're talking about KSP, as in the K for dissolving an ionic substance. If Q is equal to K, then that means your system is at equilibrium, which means that you have a saturated solution. Okay. If your Q turns out to be a little bit greater than K, or KSP, remember that Q or K, that's the product concentration over the reactant concentration raised to the power of their coefficients. So if that expression is too large compared to what it should be at equilibrium, because remember K is what it should be at equilibrium, that's going to eventually reach that value. Q is where you are right now. So if where you are right now is too large, that means you have too many products. And so if you have too many products, that means that the reaction would proceed to the left in order to reach equilibrium. And if it's proceeding to the left, remember you have your solid going to your aqueous ions, right? So if your products are too many, that means it's going to shift to the left to make more of the solid, and therefore it's going to precipitate. So a precipitate forms. If your Q, however, is too small, so Q is smaller than what should be at equilibrium, that means this ratio is too small. So you can think of it as not enough products or too many reactants. So here you have too many reactants. If you have too many reactants, that means the reaction needs to proceed to the right. If you have too many reactants going to go this way towards the aqueous ions, so it's going to form more aqueous ions or dissolve more. And so no precipitate would form. And so if you have an ionic substance and you're trying to figure out whether you will have a precipitate or not, you could use Q to compare it to KSP. And we've done that before. Let's practice a few of these. So the first one here, it says we have nickel 2 ion, and they give us the concentration of it. And a solution of sodium carbonate is added to that nickel solution, where the carbonate ion is given to us. So we're mixing nickel 2 plus with sodium carbonate, and we're asked where will there be a precipitate. Well, the first question you ask yourself, what kind of precipitate would form? And the answer is nickel carbonate. If there is a precipitate, it would be nickel carbonate for two reasons that you would know that. If you're adding nickel 2 plus and sodium carbonate, we know that sodium salts will always be soluble, and so when you combine those two, the only substance that could be slightly insoluble would be the nickel carbonate. The other reason that you would know that is because they give you the KSP for the nickel carbonate. So if you ever have to predict whether a precipitate forms or not, they usually will give you your KSP value. So the second thing you want to do after you figure out that it's nickel carbonate is write out your dissociation equation for the nickel carbonate. And then your KSP expression. Or in this case, you might want to actually call it, I would probably call it Q because we're trying to figure out where we are right now. So I'm going to call it Q. is the concentration of the Ni2 plus and times the concentration of the CO3 2 minus. And I'm going to calculate Q and compare it to my K or my KSP. In this case, it's pretty simple. They just give you the concentrations of both. And they're not the same number. And the reason for that is they come from different sources, so they will not be the same amount. It's not like we're dissolving just nickel carbonate in there. If nickel carbonate forms, it's from the reaction of the nickel ion plus the sodium carbonate. So anyway, here are my values, 6.0 to -4th molar. My Q ends up being 9.0 times 10 to the -10th. And so once you calculate your Q, you compare your Q with your K. So let's see, my KSP is 6.6 times 10 to the -9th. My Q is smaller than that. So Q is smaller than KSP, which means what I have right now is too small compared to what it should be at equilibrium. So my product to reactant ratio is too small. That means that I'm going to proceed to the right for the reaction to reach equilibrium. Proceeds right, which means I'm going towards the ions to form more ions. More of it dissolves, and so no precipitate would form. Let's try another one. So suppose you mix 10 milliliters of 0.02 molar BaCl2 with 5 milliliters of 0.03 molar sodium sulfate. Will a precipitate forms? And they give us the KSP for the barium sulfate. So that kind of tells us if a precipitate forms, it's going to be barium sulfate. The other reason why we would know that is because sodium salts are all soluble. Chloride salts are typically soluble, but that's not one of the rules that you had to memorize. Anyway, since they give us the KSP or the BaSO4, we know that. So we'll write the association equation for that. And if we want to figure out if the precipitate will form or not, we're going to write our Q expression, and we're going to solve for it and compare it to our K. So here's my Q expression, concentration of the barium ion times the concentration of the sulfate ion, and I need to plug them in. Now the barium would come from the BaCl2, but it is not 0.02 molar. And the sulfate is going to come from the sodium sulfate, but it is not 0.03 molar. I don't plug in 0.03 here and 0.02. Why not? Because I'm mixing two solutions. Once I mix the two solutions together, then my volume changes. So in my flask here, what I have is 10 milliliters of my BaCl2, and I have 5 milliliters of my Na2SO4. And so the total together of my solution is 15 milliliters. So I need to figure out how many moles of each and divide by 15 milliliters to figure out what the concentration is. So I'll do that down here. So if I want the concentration of the Ba2 plus, what I would do is I would say, well, I have 10 milliliters, so 0.01 liters times 0.02 moles per liter of Ba2 plus, and then I would divide that by 0.015 liters. And that gives me 0.0133 molar of the Ba2 plus. You could also, if you prefer, you could do an M1V1 equals M2V2. You could do that. The next one is my sulfate ion. And so I have 5 milliliters of that, which is 0.005 liters times 0.03 moles per liter of sulfate. And then divide that by 0.015 liters. Again, you could always do M1V1 equals M2V2. I get 0.010 molar of the sulfate. So now that I have that, I can plug it in back into my Q expression. So my barium ion concentration was 0.0133 molar. My sulfate is 0.010 molar. Hopefully you can do this without a calculator. It's 0.000133, which, I mean, you can already tell that it's larger than my K. So let's think about this. My product to reactant ratio right now is too large compared to what it'd be at equilibrium. So if it's too large, that means I have too many products. So it's going to shift to the left to make more solid, and therefore a precipitate does form. And so that's our answer. All right, so far that was review. We did that in the equilibrium chapter a couple chapters ago. Now we're going to add a little bit to that. So suppose that you are mixing two solutions like we did in the last problem, and they want to know whether a precipitate will form or not. So we do what we did, we get Q. But then what if that's not all they wanted? What if they're asking, what would the concentrations be after a precipitate forms? So let's look at this question. It says, calculate the equilibrium concentrations of Pb2 plus and I minus in a solution formed by mixing 100 milliliters of 0.05 molar lead nitrate and 200 milliliters of 10th molar NaI. So I have my beaker or my flask, and I'm mixing 100 mils of the PbNO32, and I'm also mixing 200 milliliters of the NaI. Okay, now missing from that is our KSP. You would have to be given what the KSP is. Now, if a precipitate forms, what precipitate would it be? Well, we know that anything with nitrate and anything with sodium would be soluble, and so we'd be left with lead 2 iodide. That would be our only option. And again, if this was on the exam or on the test, you'd be given what the KSP is, so you would know. So let's actually add that. The KSP for PbI2 is equal to 8.7 times 10 to the negative 9th. All right, so what would happen is the I minus from the NaI reacts with the Pb2 plus from the lead nitrate, and maybe a precipitate would form. We don't know. So if we want to know if a precipitate forms, what do? We calculate Q. So let's write out our steps for this reaction, or for this question, because it's kind of long. So the first thing we want to do is, if we want to determine the concentrations at the end, we want to determine if a precipitate forms or not. Because if a precipitate forms, it's going to take away from the ions that we have in our solution, right? And so we are going to determine first if a precipitate forms. So we write our dissociation equation here. So Pb2 plus solid would dissociate into Pb2 plus and 2I minus. We'll write our Q expression so we can compare it to the K. It's the Pb2 plus concentration times the I minus concentration squared. we're going to plug in our values, but just like last problem, we can't just plug in our 0.05 molar and our 1/10 molar, because once you mix them, your volume changes. Now we have 300 milliliters. And so you can use M1V1 equals M2V2, or you could find the moles and divide by the total volume, whatever you prefer here. So I'm going to do that on the side here. So I will start with the lead ion. So I have 0.100 liters times 0.05 molar of the Pb2 plus is equal to M2 times 300 milliliters. And the Pb2 plus concentration right now is equal to 0.0167 molar. I'm going to do the same thing with the other one, so 0.200 liters of the 1/10 molar I minus equals M2 times 300 milliliters. And I end up with the I minus concentration being 0.0667 molar. So I'm going to plug these values into my Q expression. So 0.0167 molar, and then my I minus is 0.0667 molar, but don't forget there's a squared there. My Q ends up being 7.43 times 10 to the negative fifth. I'm going to compare that to our K, so our Q is larger than our KSP, which tells us our product to reactant ratio right now is too large compared to what it would be at equilibrium. So if my products are too many, that means it's going to shift to the left to make a precipitate, and therefore a PPT forms. Now, if this was not true, what if Q was less than our KSP and no precipitate forms? Then we're done with the problem. If no precipitate forms, then these are my concentrations at equilibrium. We're done, right? Because these are the ions that are swimming in the solution, nothing precipitates, so we would be done. However, because now we know there's a precipitate that forms, the equilibrium concentrations of these ions will actually be less than these, because some of these are going to get used up in order to make the precipitate, and they're going to fall out of the solution, and so the solution will have these in a lower concentration, and so we need to figure out how much lower. So your second step here is going to be to find the concentration of the ion remaining as excess after the precipitate forms. Meaning that one of these is a limiting reactant for me, so I need to figure out how much of these react together to form the precipitate and how much is left over in order to dissociate or participate in my equilibrium. So what you're going to do is you're going to look at your two ions that would react to form a precipitate. So Pb2 plus 2I minus would form precipitates here. And this is 0.0167. You can do this in molarity or in moles. It doesn't really matter since, you know, the volume is the same. So between those two, which one is my limiting reactant? Well, even though I need twice as much of this as this, I have way more than twice. I have like almost 5 times or so more of this than I do that one. So it looks like the Pb2 plus is my limiting reactant. And so that's how much I'm going to use up of it. I use up all of it actually. And then for the I minus, I'm going to use twice as much as my Pb2 plus. So minus 2 times 0.0167 is 0.033 molar. And so that's how much is going to be used up to form my precipitate. So at the end, I'm going to be left over with 0.0333 molar I minus left as excess. Alright, so far I figured out that when I mix these two solutions, some of the Pb2 plus and the I minus react together to form a precipitate. Turns out my lead ions are my limiting reactant, so I use all of these up. I use some of the I minus, and I have some I minus left over. So then my third step would be to actually answer my question, which asked for the equilibrium concentration. So that's going to be my third step here. Find the equilibrium concentration. So to do that, we are going to look at our salt that would dissociate again. And in this case, since I'm trying to find equilibrium concentrations, I'm going to do an ice chart. Don't care about my solid here. So, what's going to happen is that the Pb2 plus and the 2I minus are going to react together to form my precipitate. I use up all my Pb2 plus, and so I don't have any of it, but I do have some extra I minus, and so these are going to be my initial concentrations here for my equilibrium. So this is 0, this is 0.0333 molar. Some of this precipitate would dissociate to form some X of this and some 2X of this, and so at equilibrium this is X, this is 0.0333 plus 2X. I write my KSB expression next. Concentration of the Pb2 plus times the concentration of the I minus squared. My KSB is 8.7 times 10 to the negative 9th. That is equal to X times 0.0333 plus 2X. Don't forget that that quantity is squared. And since there's no division here, you don't really need to graph it and find the intersection there. You can just use simple algebra. But X ends up being my, or it ends up being 7.8 times 10 to the negative 6 molar, which in this case is the Pb2 plus concentration at equilibrium. And so that's one of my answers. If I wanted my I minus concentration, that's going to be 0.0333 plus 2X. So 0.0333 plus 2 times the 7.8 times 10 to the negative 6, which ends up being, X is too small, it ends up being 0.033. Now, this is a really long question. I highly doubt that any of this would be on the AP exam. Maybe the first part there where you were asked whether would a precipitate form or not. It is fair game for my test, but for the AP exam, they are going away from complicated math calculations, which obviously this one is, and they're going to simpler calculations and more conceptual stuff, so you will not see something like this on the AP exam, I guarantee you. So what would be an application for this? Well, qualitative analysis is a lab method that is used a lot for different things, and one of the things is to identify different ions in solution. And so we use the solubility rules to kind of narrow things down, react them with different things, see if precipitate forms or not. That kind of tells us or identifies different ions. So, for example, let's say that you have a solution that contains Ag+, Pb2+, and Cu2+, and you want to know, you want to separate them, or you even just want to know whether all three of these exist in your solution or what. So how would you go about doing that? Well, we know that silver chloride and lead chloride are insoluble or sparingly soluble. So a good way to separate these two from the copper 2+ would be maybe to add a source of chloride, like maybe HCl or NaCl or something like that. So if I add NaCl, then the AgCl2 and the PbCl2 would precipitate out, and what you would be left with in solution would just be your copper 2+ ions. So that's one way to separate the copper 2+, and then you can compare the different solubilities of the AgCl2 and the PbCl2 and kind of add a little bit of water, or maybe even heat up your solution. The PbCl2, if it's a saturated solution, will dissolve in hot water, but the AgCl2 will not. So you could, after you separate your precipitate, then heat up your mixture and add a little bit of water, hot water, and the PbCl2 will dissolve, and then you can separate it from your AgCl2 solid. So that's a way to identify or separate substances using solubility rules. Let's try a problem here. It says, suppose that you mix 0.01 molar NaCl with 0.001 molar K2CrO4, and you add a solution of AgNO3 slowly without appreciably changing the solution volume. Which one would precipitate first? So let's first figure out what could precipitate before we figure out what could precipitate first. So we have a beaker. We have NaCl, so let's dissociate the ions so it's a little bit easier to look at. So we have Na+, we have Cl- is from the NaCl. Then we're adding potassium chromate, which has K pluses and CrO4 2 minuses. And then to that, we're adding a solution of silver nitrate. And supposedly that's going to make something precipitate out. So we want to know what would precipitate first. Well, let's see. So obviously, whatever the precipitate is something that's positive combined with something that's negative. So let's see. Anything with Na+, we know for sure is going to dissolve, because that's any salt with sodium is soluble. Same thing with potassium. Anything with potassium ions is soluble. And same thing with nitrates. All nitrate salts are soluble as well. So that leaves us with Ag+, CrO4 2 minus, and Cl minus. So we have two options. It could either be AgCl, or it could be Ag2CrO4. These are the two options. Now, you could compare their KSPs, but that's not enough, because remember, if they were the same ratio, like, let me write the dissociation equation to explain. So this is Ag plus and Cl minus, solid there. This one is 2Ag plus and CrO4, 2 minus. So if both of these were, like if all the ions were the same concentrations, and this was a 1:1:1, and this was 1:1:1, like they were the same ratio, then you can just compare KSPs. But in this case, we cannot just compare KSPs for two reasons. First, the ratios are not the same 1:1:1, but this one is 1:2:1, so that wouldn't be okay. Moreover, my Cl minus concentration is not the same as my chromate concentration, and so that would not work either. So for both of those two reasons, you cannot just compare KSPs. So what do you have to do? You have to figure out, since you're adding the AgNO3 in order to precipitate it, basically what's making it precipitate is the addition of the Ag+, right? So you have to figure out at what concentration of Ag+ would this start to precipitate, and at what concentration of Ag+ would this one start to precipitate. Well, they would start to precipitate when we reach a saturated solution, which means when your concentrations multiplied together would equal to your KSP, right? So let's write our KSP expressions here. KSP is equal to concentration of Ag+ times the concentration of the Cl minus. And here, KSP is the concentration of the Ag+ squared times the concentration of the chromate. Oh, yeah. All right, so what's common between them again is the silver ion concentration. So I want to solve for what that would be in order to precipitate. So my KSP for the silver chloride, let's start with that one, is 1.8 times 10 to the negative 10th. And if we say that X is going to be the concentration of the AgCl when it's a saturated solution, then, well, actually we don't need to do that because we have the Cl minus concentration, so never mind. We can just solve for this. So if we want to know what the Ag+ concentration would be, we plug in just the Cl minus concentration there. It is 0.010 molar, and so hopefully you can do this one by hand. The Ag+ concentration would be 1.8 times 10 to the negative 8th molar. So when I reach this concentration of Ag+, my AgCl starts to precipitate. Let's do the other one. So my KSP for this one is 1.2 times 10 to the negative 12. So that's equal to the concentration of the Ag+ squared times my chromate, in this case, was 0.001 molar. And so if you solve for the Ag+, remember you would divide by 0.001 molar and then take the square root of that. That ends up being 3.46 times 10 to the negative 5th molar. Now let's think about this for a second. In order for this to precipitate, I only need my concentration of the silver ion to be as little as 0.000000018 molar in a liter. In order for the silver chromate to precipitate, I need my concentration to be 0.00003, let's say 5 molar. So this would precipitate at this concentration or anything higher. This would precipitate at this concentration or anything higher. So which one would precipitate first? This one right here. AgCl precipitates first. Because very little of it, I only need very, very little of it before it starts precipitating. This one, I can keep the, silver chromate, I can keep adding until I reach this before it will precipitate. All right, next question says, what is the chloride ion concentration when the Ag2CrO4 begins to precipitate? Let's think about this for a second. So when would the Ag2CrO4 begin to precipitate? Well, it would begin to precipitate when this is the concentration of the silver ion. Let's write that down first. So the Ag2CrO4 begins to precipitate when the silver ion concentration reaches 3.46 times 10 to the negative fifth molar. So if we want to figure out what the chloride ion concentration would be, well, the expression that we have the chloride ion concentration is this, and so we can plug in this value for the silver ion concentration into here to figure out what the chloride would be. All right, so I just wrote that down. This says the Cl minus concentration when the Ag plus concentration has reached this value can be calculated from the KSB for AgCl. So let's actually try to do that. So I'm going to write down my expression for the AgCl. So the AgCl solid partially dissociates into Ag plus and Cl minus. My KSB expression again is the concentration of the Ag plus times the concentration of the Cl minus. And my value for the KSB is 1.8 times 10 to the negative 10th. And so that when the Ag plus is 3.46 times 10 to the negative fifth, we can calculate what the Cl minus would be. And in this case, the Cl minus is going to be 5.20 times 10 to the negative 6 molar. And that's my answer right here. And that is the end of the buffers chapter, finally, the aqueous equilibria. I know it was a really long chapter. It's the hardest chapter, so hopefully from now on it's going to be a little bit easier. Have a great day, guys.